in meters, or it could be time in milliseconds or microseconds, or it could also be the delay. Okay, fine. So we were discussing the measurement metrics, right? It could either be distance, or it could be time, or it could be number of hops also. Okay, it could also be number of hops. That is also a distance. That is also a measurement metric. So we've studied in detail as to how you can find out the shortest path from one point to another point using Dijkstra's algorithm and using Bellman-Ford algorithm. Now moving further, there is one important disadvantage that is there in the case of Bellman-Ford algorithm, and that is one is the count to infinity problem. Okay, wherein it is something like it is also equivalent to say that good news propagates very fast and bad news propagates, it takes its own time, it is lethargic to propagate and all that. Now what does it mean? Just look at these two diagrams given here. Just look at where my cursor points to. Let us say this is it's a very simple network for you to understand. You have got the network has got 5 nodes, A, B, C, D and E. Okay, now initially the distance on each link, or the distance of each link, is 1. Okay, so that is why there is no number mentioned. A to B, the cost is 1, B to C cost is 1, C to D the cost is 1, D to E the cost is 1. Okay, so initially you can observe here, this is with respect to A, right? So with respect to A, initially A does not know the distance to any of the other nodes. Now after one exchange, what does this exchange mean? It is something to say that A exchange, let us say, a hello message. It sends a hello. So who receives it? A is connected only to B. So B receives it, right? So B sends it, and that's how it, after all this, it understands that the distance to B is 1. And then B to C, the distance is 2. Isn't it? Sorry, B to C, the distance is 1. And thereby A to C, the distance would be 2. Then again, C to D, the distance is 1. Then, so therefore A to D, what would be the distance? It would be 1 plus 1 plus 1. So it would be 3. Similarly, to E, it is 4. Okay. Now let us say this is what happens after some 4 exchanges. Now look at the other one, that is, look at this particular figure. What you understand from this is, you observe again, initially what is it that A has decided? A has got the distance to B, C, D and E. And what is the distance? It is, to B it is 1, to C it is 2, to D it is 3 and to E it is 4. Right. Now let us assume that the link between A and B has failed. Okay, so you assume that the link between A and B has failed. This particular link is not existing. Then what happens? What happens next? How does it go about? Now A to B, there is no link. Okay, now let us say B tries to find out the distance to A. B doesn't know that. Let us say it tries to update its table, so therefore it tries to find out the distance to A. Then what happens when it tries to find out, or when it tries to update, it sees that it is unable to reach A, right? Somehow it is unable to reach A directly. So then what does it do? It has to find out with its neighbor. And who is its neighbor? C is its neighbor. Right? C is its neighbor. So what does C say? C says, hey, come on, it's okay. I have the distance to A, which was existing from the earlier exchange, and the distance in my table to A is 2. Right? It is 2. So now what does B update its table as? It finds out that the distance from A to C in C's table is equal to 2 plus the distance from B to C in its own table is 1. So 2 plus 1 gives it 3. Right? It becomes 3. Correct? The rest is remaining as it is. Right? So next, again, let us say again it tries to find out. Again it sees that it is the link is not there. So therefore it C has to try and update. Right? When C tries to update, what does it update as? It finds out that B has a table, and in B's table the value of A to B, the link value is 3, and again B to C the value is 1. So it updates its table as 3 plus 1 equal to 4. So this is after 2 exchanges. Similarly, after 3 exchanges, there is an increase again, 7, 8. So what happens is, every time there is an exchange of hello packets, exchange of routing tables, the value goes on increasing. Why? Because none of them are really they do not know that the actual problem is that the link between A and B has failed. Okay, A is not existing in the network anymore, but just look at the table. The cost to A goes on increasing after every exchange. This is known as count to infinity problem. Now look at this, another example. You can just see this is another count to infinity problem, again with 1, 2, 3 and 4. The same, let us say. Now here we've got only 4 nodes. Right? So we have node 1, 2, 3 and 4, and again the distance of each link is just 1. So now what happens before there is any break or anything like that? What would the values in the routing table be? That is what will be it's what is shown here, right? That is in the first row. What happens to node this is what is that? The destination is node 4. Correct? So from 4, if it has to reach node 1, what is the total distance? It is 3, and etc. Now let us say there is a break, that is there is a break between 3 and 4. Then what happens? Every time it has to go on updating its table. Therefore, every time it goes on increasing its value by the distance that was existing earlier. Correct? So therefore, it is known as counting to infinity problem. Okay. So this is again, this is one more example. The update to update the routing table for the following topology after the link breaks. This is an example that you can solve. Okay. Here there is a break in the link between B and C. Then what happens? How is the routing table going to be updated? That is what you have to find out. Okay. Now, in order to solve this problem, so the solution to this is, there are two solutions or two remedies. One is the split horizon method and the other one is Poisson's reverse. Now in the split horizon method, you do not report route to a destination to the neighbor from which the route was learned. That is, now let us say I have learnt from you. You have the distance to some other node and I have learnt it from you and I have updated it. Then I should just stop it over there. I should not update the same thing to you once again. Oh, right? So based on what I have is already based on what you had earlier. Now again you're updating using what I'm sending to you again. So this is going to cause an infinite loop, right? So the split horizon method says that you don't report the route to a destination to a neighbor from which you had learned the route earlier. Or the other one is the Poisson reverse, when you report a route to a destination to the neighbor from which the route was learned. But what you do, you give it as infinite distance. And then therefore automatically when you give it as infinity, it automatically breaks the loop, right? When it is infinite, it does not enter into the loop because it does not know what it is going to be at all. Okay, then okay, now this is how you are going to use the solution, the split horizon. What does it do? Now before the break, the node 1's table, it had 2, 3, and node 2 had got 3, 2, and node 3's table had got 4, 1, right? So that means this is with respect to node 4. The distance to node 4 from node 1 is 3 and it has to go through node 2, right? Similarly, node 2 had its table updated as this. If it has to reach node 4, the total distance was it had to reach through node 3 and the total distance was 2. Now similarly from node 3 to node 4, what do you see? The distance is 1 and it is the destination itself. This was what was happening before the break or before the link failed. After the link failed, what happens? Now the link has failed between 3 and 4, isn't it? So which node has to update immediately? It is node 3. Now what would node 3 update as? It is now, since it does not find the node 4, we'll just observe what is given here. Just read it. Node 2 advertises its route to 4 through node 3, isn't it? We know that node 2 reaches node 4 through node 3. 2 reaches 4 through 3. But what happens here? 3 is giving it as infinity. 3 says the distance is infinity. So that means node 3 sees that there is no route to node 4 at all. Isn't it? Now, as soon as this happens, which is the previous node? It is node 2, or which is a neighbor to 3? It is node 2. Node 2 also updates its route to node 4 as -1, infinity. Okay, and after this is seen by node 1, node 1 is also going to update as -1, infinity. So therefore in just 3 steps, all the other 3 nodes that are there in the network now know that node 4 is not reachable. Okay, unlike what was there earlier. Just look at the same problem. This was it, right? Just look at what is happening. You start from the right hand side so you understand better. Now we are looking at node 4. We are looking at all the other nodes with respect to node 4, right? So how does it reach node 1? Node 1, it has to node 1 reaches node 4 through node 2 and its distance is 3. Similarly, from node 2 the distance is 2 and from node 3 the distance is 1. Okay, now after the break, what is happening? Now node 1 has got nothing to do with it because it doesn't know anything. Node 2 also doesn't know right now, but anyway, look at node 3. Node 3 does not know what it is to node 4. So what does it do? It asks its neighbor. It asks its neighbor if it has got a route to node 4. Then what happens? Node 2 had its distance as 2, isn't it? It had an entry to node 4, which got transmitted, or that would be shared, isn't it? So it shares that the distance to node 4 is 2, isn't it? The distance to node 4 is 2. And similarly, or the distance is 3, whatever it is, it keeps on getting what is it? It keeps on getting updated. The distance from node 2 to node 4 in node 2's table was 2, and again 2 to 3 the distance is 1. Therefore it updates it as 2 plus 1, that is 3. And through which node? It is through node 2. Okay, so now this iteration is done. The next iteration, what will it do? Again it starts, 3 is going to send it to 2, 2 is going to send it to 3, 3 sends it to 2, and 2 sends it to 3. So again and again it keeps on updating, isn't it? But how does split horizon serve? How does it what do you say, rectify this issue? By making the value as -1 comma infinity. It makes the distance as infinity. Therefore, in lesser number of iterations, all the nodes in the network know that the node is not reachable. Okay. Next. Now another concept in network layer is that of flooding. What is flooding? Flooding is done so that the network is sure, or it is to ensure that all the nodes in the network are definitely going to receive this particular piece of information or data from one or the other node. Okay, so what it does, what is flooding? It's very simple to understand. Flooding is wherein you're going to flood the network with the pieces of information, or with the chunks of data or packets. So how would you do it? You're going to send the copy of the same packet. You're going to send copies, multiple copies of the same packet through all the outgoing lines, right? So you observe here, 1 is going to send that packet from, it is connected to 3, it is connected to 4, and it is connected to 2. So whoever may be the destination, irrespective of the destination, it is just going to send that data to all the lines. It's going to send it on all the lines. This is flooding. Okay, so then what happens? What should the routers do once they receive it? Now, from 1 it was sent to 3, it was sent to 4, and it was sent to 2. Correct? So now 3 has received these packets. What should 3 do with it? Node 3 is going to further send it on all its lines, but the only thing is it will not send it on the line that it received it from. Okay, so it's just as simple as this. I am the source of information. I put it through all my contacts. Okay, and then those contacts who received it from me are going to further forward it to all their contacts, but to me. So they do not send it back to me. Okay, this is called as flooding. So therefore this network is very certain that the destination is certainly going to get it. Okay, so even if one particular network, or if one particular link in between fails, even if any link fails in between, the packet has definitely reached the destination through some other route, right? So instead of finding the shortest path and that and this is also another method that is done. This is called as flooding. Okay, so but what is the disadvantage of this? Let us say, for example, all the lines through which the network, through which the data was sent were working fine. So what happens? The destination has received the same packet or multiple copies of the same packet multiple times, isn't it? From all its incoming lines, it is going to receive the packets. Correct. So some certain another variation to this flooding is limited flooding, wherein the time to live field in each packet limits the number of hops to a certain diameter. Now this you might have come across. There is something called time to live field. When you say, for example, you ping using your system, right? You go to the command prompt and you say ping, you ping some website or you ping some IP address. Then you must have observed something called TTL. It says time to live, and it also gives you the number of hops. Okay, that is something you can observe. Now, what is a time to live? Time to live is the maximum time that that particular packet can live in the network, after which it's just destroyed or it is not forwarded to any other router anymore. Okay, something like an expiry date, right? So if at all I have, if I have a medicine with me and its expiry date or it has already expired, would you want to forward? Would I want to forward? No. In fact, even in case I get it or I send it to you, you stop it over there. You don't forward it. That is time to live. Okay, so you don't allow you don't allow the packet to keep moving unlimitedly or indefinitely. Now, each switch adds its ID before flooding, therefore it discards the repeats. And then the source puts a sequence number in each packet, and it switches records and switches will record source address and sequence number, and it discards the repeat. Now, why is this done? If let us say we are trying to send it, right? All of us are trying to send. If I have already received the same packet from some other source, from other line, so it is the same packet, right? It is a packet from the same source which I have already received from another line. Then I understand that it is a repetition, so I'm not going to forward it anymore by looking into these data or these this information. Okay. Moving further. Now, another very important routing algorithm that we use, this is in fact used most of the in networks today, is the distance vector routing algorithm. What is done here is, again, distance vector routing algorithm is based on the same concept that we have done earlier, but the way in which it makes its table would be a little different. What it does here is it constructs a one-dimensional array containing the distances or the cost or weight, whatever it is, right, to all the other nodes, and it also distributes that vector to its immediate neighbors. Now this is a word that I used in my previous class also. Vector is nothing but the table. Okay, it is a routing table, is also the routing table is also known as a vector table. Fine. So what does it do? Now I have to find out, I have to find out a route to some particular node, which I do not know. I do not know the route. So then what do? I will ask my neighbors if they have the route to it. So by doing so, by say, what do you say? By distributing the routing tables to all the nodes in the network, every node would know the distance to every other node in the network. Okay, this is distance vector routing algorithm. Here there are some initial assumptions. Now each node knows the cost of the link to each of its directly connected neighbors. Instead of taking it as infinity initially, here we assume, it is assumed that the direct contacts are already known, and then if a link that is down, a link that has failed, that will be assigned an infinite cost. Okay. Now look at this. This is a distance vector routing algorithm. Just observe here. This is the network that we have got. Fine. So what is the information that will be stored at each node? A, B, C, D, E, F, and G. Right. So what does A have? A to A, it is 0. A to B, there is a direct link, so it's 1. A to C, A to C, there is a direct link and its value is 1. A is not connected to D directly, so it keeps it as infinity. And in fact, rather infinity, it does not know what it is. Correct? So that is how this table is constructed. This is the initial distances that are stored at each node, right? So A to A, this is nothing but the same cost matrix that we had written earlier with respect to Dijkstra's algorithm. Fine. So this is also known as a global view, right? It's also known as a global view because you're getting the distance from each node to every other node of the network. It's a global view. Now, so what is it that is important here? Every node will send a message to its directly connected neighbors containing its personal list of distance. Okay, this is something like, let us say I have a contact list and I share my contact list with whom? My contacts, isn't it? I have a contact list and I can share that contact list with my own contacts alone. Now what would they do? What will they do? They will check who their contacts are from the list that I send and who their contacts are, who are not their contacts from my list, and they are going to update their list accordingly. Correct? That is what is given here. I hope this point is clear. Okay. So then what happens after every node has exchanged a few updates with its directly connected neighbors? Now what happens? Finally, all the nodes will know the least cost to all the other nodes, because what I am sharing with you itself is the least cost to my neighbors, right? You are going to use that to find out the least cost to your neighbors also. So therefore, you have the least cost to my neighbors as well as your neighbors. That's how you're going to build your network. Okay. Now, in addition to updating their list of distances when they receive the updates, the nodes will also have to keep track of which node told them about the path that they used to calculate the cost. Why is it important? Because they should know where the update came from. Okay. Now, this is the example. This is the final distances stored at each node. How do you get this? What was there earlier? The earlier table was this, isn't it? Wherein A knows only its neighbors, B knows only its neighbors, C knows only its neighbors, and so on. Now A has shared its node, its vector with B. Let us say A has shared its vector with B. What would be update? What would be update with respect to A? You observe A also does not know the distance to D. B also doesn't know the distance to D. B doesn't know the distance to E also. But A knows the distance to E. And what is it? It is 1. Right? A to E and A to F. The distance is 1. Now based on this, can B not write its table? B knows that the distance from B to A is 1. Distance to B to A is 1. And therefore, distance to E through A will be how much? It will be 2. Isn't it? 1 plus 1, 2. Similarly, the distance to F through A is going to be 1 plus 1, that is 2. Right? So that is what is given over here. B to D and B to E. Correct? Similarly, B would have received the table from C, D, E, F, G, whoever its neighbors are. Correct? Based on all this, it is going to make its own table. And this is the global view. That is the final distances that are stored at each node. Okay, this is the final that is stored at each node. Now, how else can this be constructed? Right now, I told all this is just 1, 1, 1. So it was easy for me to find out what the value is. But if it is a different value, then what should you do? Remember, distance vector routing algorithm makes use of Bellman-Ford routing. Okay, it makes use of Bellman-Ford routing. So if A has to find out the distance to D, what will it do? It can use Bellman-Ford algorithm to find out the distance, right? So that is how each node is going to update its table. And with all these tables put together, you get the final distances stored at each node, which is the global view of all the distances. Okay, now I hope you have understood this. This is what I told you. This is a routing table maintained at node B. Do you understand? From B, the cost to A is 1, cost to C is 1, cost to D is 2, 2, 2 and 3. What is the next hop? What does that mean? What is the next hop? That means in order to reach, say, E, if a packet should reach E from B, it has to go through the node A. This is the next hop. It has to go through the node A. Okay, so these are the three columns in a routing table: the destination, the cost to that destination, and the next hop that has to be taken in order to reach that particular destination. Okay, so in case, let us say you are asked to find out how can you expect this in your exam? What can you expect? You may be given a network like this, and you will be given the cost to the other nodes and all this. You will be asked to give us the distance vector routing table, both the initial views and the global view and all that, initial distance and the global distance. So then this is what you have to do. You have to give this table, this and whichever you are writing, or if in case you are asked which particular node, then that particular node. Okay, this is what is distance vector routing algorithm. Oh, I'm going back. Okay, now there is another similar algorithm which is known as link state routing algorithm. Link state routing is more about flooding. It makes use of flooding. The basic idea here is for a node to send its link state information on all its directly connected links. Now let's just see what it does. There is a packet known as a link state packet. Okay, the link state packet will contain the ID of the node that created the link state packet, and it has a list of the directly connected neighbors of that node. It also has a sequence number and a time to live for this packet. Now what is it that each router does with all this? It should first, now let us say you are fixing a router and it has just turned up. You've just turned up the router. You've just turned on the router. Then what is it that the router should do? It has to find out who its neighbors are, and it has to ask for its neighbors' network addresses, and then it should measure the delay or the cost to each of its neighbors. And then with this, it has to construct a packet telling all that it has learned. What has it learned? It has found out who its neighbors are, it has found out their network addresses, and it has also found out the delay or the cost to each of its neighbors. So this packet that it constructs, it has to send to all the routers or to all its neighbors. From there, again, each neighbor is supposed to compute the shortest path to every other router. Now this is an example of a LAN. So here each of them have to find out who their neighbors are. Okay, after finding who their neighbors are and all that, it has to measure the delay or the cost to each of its neighbors. This is what is the link state packet. Something very similar to what we have seen earlier. Just see that it has two extra entries, which is known as sequence number and the age. Now why this is important is because it should know. Now these are all updated periodically. Okay, it is all periodically updated. When you're updating periodically, you should know which is the latest information, isn't it? You must know which is the latest information. So for the router to understand which is the latest information, it is going to make use of this sequence number. Okay, and so what does it now? You see A has got two neighbors, B and E, and the distance to B is 4, the distance to E is 5. Similarly, you look at B. This is the link state packet of B. B has got 3 neighbors A, C and F, whose corresponding distances are given over here. Okay, similarly all of them have constructed their link state packets. So how is it distributed? It is by making use of sequence numbers to avoid duplicates and use the age or time to live of a packet. So this is the packet buffer for router B, right? So what does it do? It has to compute the shortest path to every other router by making use of the table that it has received from all the routers. Okay, and then it sends something known as some flag signals or flag messages, which means that the packet must be sent on the indicated line. The acknowledgement flags mean that it must be acknowledged over there. That means what? Let us say A, it has received, B has received a link state packet from A whose sequence number is 21 and the age is 60. Say 60 milliseconds. It can keep that packet only for 60 milliseconds. It has to send these flags to A, C and F. And if it has to send to A, the distance, and these are the acknowledgement flag. The acknowledgements must be sent to this. This is what it is. Okay, this is a packet buffer for router B. And if you look at this is just the same thing. So what we've done earlier, what we've done so far is we have done distance vector routing, which makes use of Bellman-Ford algorithm, wherein we have found the routing control overhead linearly increasing with network size. Why it increases with network size? Because more the number of routers in the network, more will be the number of entries in each table, in the table of each router, and therefore the complete global view would be very, very large. Okay, and then convergence problems. What is the convergence problem? Again, count to infinity, because again we are making use of Bellman-Ford algorithm. So if there is a link failure, automatically the network might end up in an infinite loop, and this infinite loop is what is known as given here as potential loops. There is a very high chance that the routing tables might end up in a loop. Okay, and then link state routing is used in a protocol known as OSPF. It's called as Open Shortest Path First. This is one of the protocols that is currently in use in our networks of today. Okay. In this case, the link updation flooding, it is done by flooding, and the overhead caused by frequent topology changes. Every time there is a change in the topology, every time a link state packet has to keep being sent, and also periodically also they keep sending them, and therefore the overhead is automatically going to increase. What you can note here is conventional routing does not scale to size and mobility. Okay, so this is what we have done in today's class. We will see this in our next. This is the wired networks. This is the case for wired networks, whereas wireless networks, the table updation would be very periodical. Okay, and hierarchical routing we will see in the next class. Is that fine? I hope you could all understand today's class. This class was very short. I see that okay. Yeah, so I hope you've all understood today's class. Let me just stop sharing the screen. Before that, let me just download the attendance. Well, okay, so I hope you could all solve today's quiz as well. It was all based on data link layer, right? And you must have received the instructions about your lab and all that. In case you haven't, you need not really worry. It will be scheduled someday. If there's anything else you want to ask, you may go ahead. Yes, anybody wants to ask anything? Okay, there's nothing, then we should. Why would you want to mute my microphone? Fine. Okay then. All of you have a good day. Have a great weekend. See you in the next class on Tuesday. Okay, Tuesday we have a class in the morning, right? 8 to 9:30. So see you all on Tuesday morning at 8 o'clock.
Thank you, ma'am.
Have a good weekend.
Thank you,
Stay
ma'am.
home, stay safe.
Thank you.
Thank you, ma'am.
Thank you, ma'am.